Welcome back. We're going to do a little short video on the proof of the alternating series test. So remember, in the last video, we introduced alternating series and we talked about how easy it was for an alternating series to converge. You only need to make sure that it was getting smaller and going to zero, and that is enough to say the alternating series converges. Now the question is why? And so in this video, we're going to prove why these conditions are enough to show that this alternating series converges. And so to prove a series converges, we have to do it the original way, which is considering partial sums. Now, because my series is alternating as given, and I did the n plus 1, 1, that way the first term could be positive. It's similar proof if not, doing the n1. But without loss of generality, right, we'll do the alternating series where the first term is positive. And because of the nature of alternating signs, I'm going to consider first the even partial sums. What do I mean by that? Like S2, S4, S6, S8, S2n, right? Any multiple of 2. And so that way we have a nice pairing, right? We have like the first S2 is A1 minus A2, sum of the first 2 terms. Then we go to sum of the first 4 terms. So A1 minus A2 plus A3 minus A4 out to S2n. So that's going to be out to A2n minus 1 minus A2n. That way I know where I end, right? At a plus and a minus. And in fact, let's go ahead and pair them up by pairs. A1 minus A2, and then plus A3 minus A4, plus A5 minus A6, dot, 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 plus A2n minus 1 minus A2n. Why do I pair them up like that? Is because now I'm going to use the fact that my series, or my sequence, is decreasing. That the next term is smaller than the one before it. So that means A2 is smaller than A1. A4 is smaller than A3. A6 is smaller than A5, and A2n is smaller than A2n minus 1. So that actually means when you subtract these terms, that's positive. Since A2 is smaller, I'm subtracting a smaller number from A1, and therefore it can't be 0 and it can't be negative. Well, it could be 0, right? It could be 0, worst case scenario, but it's always greater than or equal to 0. So all these terms are positive, meaning S4 is S2 plus a positive term. S6 is S4 plus another positive term. And so actually, if we look at the sequence of partial sums now, we have a monotonic sequence. The partial sums, the even partial sums, are monotonic. It is bounded below by S2, right? The smallest partial sum. It's monotonic. It is bounded below by S2. And if I can show that it's also bounded above, then I'll use the fact in 9.1 that a bounded monotonic sequence must converge to something. I don't know what it is, but I know it converges. So I know it's bounded below. Now let's see if it's bounded above. And so what I'm going to do now is I'm going to rearrange this partial sum. I'm going to write it out, A1 minus A2 plus A3 minus A4 plus A5 minus A6, dot, 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 minus what, A2n minus 2 plus A2n minus 1 minus A2n. And the reason I'm writing out a couple more terms is because I'm going to pair them a little bit differently. In this case, I'm going to leave A1 by itself, and I'm going to factor out a negative from the next 2 terms. So I get A1 minus A2 minus A3. Factor out a negative from these 2 terms, I get minus A4 minus A5. Minus dot, 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 minus A2n minus 2 minus A2n minus 1, and then minus A2n. Why do I rearrange it in this way? I'm just playing a game with negatives. Instead of pairing up the way I did, I shifted a little bit. I leave the A1 and then I pair the next 2 terms, factor out a negative. Pair the next 2 terms, factor out a negative. Dot, 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 pair these 2 terms, factor out a negative, and leave the last one in by itself. Why do I do that? Is because, again, since my sequence is monotonic, this is a positive number, this is a positive number, This is a positive number. And remember, you're assuming your sequence is positive to begin with, so a2n is something positive. And so actually, a1 minus a2 minus a3 minus a4 minus a5 minus dot dot dot, I'm subtracting a bunch of positive things. And so actually then S2n, the even partial sums are always smaller than a1. So it is bounded above by a1. It's bounded below by a1 minus a2, and is bounded above by a1. All right, this even partial sum is a1 minus a bunch of positive things, and therefore is smaller than a1. Worst case, these are all 0, so it's less than or equal to a1. And so it's bounded above by a1, it's bounded below by s2. So I have a bounded monotonic sequence. The sequence of even partial sums is monotonic and bounded, and therefore must converge to something. I don't know what, we're going to call it L. So the even partial sums converge to, say, L, to something. Now we're not done because I haven't talked about the odd partial sums. And so let's consider the odd partial sums. S2n minus 1, the odd multiple. So when it's 1, it's S1. When it's 2, it's S3. So these are the odd partial sums. Now we're not going to go through a whole proof again with that. I'm going to use the fact that the even partial sums I already know converge. And that's because S2n minus 1 is one term short of being an even partial sum. In fact, it's S2n minus it's S2n plus A2n. Right, so the odd partial sum, S2n minus 1, would stop here, but the even partial sum has a minus A2n, and so if I added in, the minus A2n would cancel with the plus A2n and leave me with the odd partial sum. Well, now all I can do, or all I need to do, is take the limit of the odd partial sums and say then that's equal to the limit of, well, the even partial sums, limits break up over addition, so I can write this, plus the limit of A2n. Well, we know the even partial sums go to L, that's what we proved, right? It goes somewhere to that L, plus, and this is where the other condition comes in, because all we've used so far is the fact that it's monotonic to show that the alternating series converge, the even partial sums converge. To get the odd partial sums converge to the same thing, that's where now it's important that the sequence goes to 0. And so if I let n go off to infinity, well, if the even terms, if all the sequence goes to 0, then the even terms are still going to go to 0. And so we'll write this down. And therefore the odd partial sums still go to the same limit L. So since now the even partial sums go to 0, the odd partial sums, the even partial sums go to L. The odd partial sums also converge to L. That means all the partial sums converge to L. We can say now all the partial sums, the even and the odd ones, both go to the same place. So the partial sums as a whole go to L. And what does that mean? That means that the series converges. Right? The partial sums converge, which means the series converges. And so this is just a quick little reasoning or proof that is showing us why with an alternating series it is enough to meet these two conditions. And why only these two is because since it's alternating, we can play some games with minuses and pluses to make it monotonic and bounded, and therefore get something convergent, where if it wasn't alternating, we couldn't play these games with minuses and plus signs and not necessarily give me that we converge. It's because we're alternating that it works. And so this was just a proof. This is not a mandatory thing to remember, but it just justifies why in the last video those simple conditions are enough for an alternating series.